So, hello everyone. I hear the church bell ring of the major church, Michel, here in Hamburg, North Germany. Welcome everyone to the International eForth 2020 meeting on Zoom. It's June 2022, and we have interesting talks today on our schedule. Our first speaker will be Klaus Schleisiek, and I know Klaus like 40 years, 35 years, and he will talk about microcore and will introduce himself probably. Yeah, Klaus.
Yeah, hello everybody. I'm programming in eForth since 1980 or 81. And I managed to always use eForth in all of my projects. And eventually, when I was absolutely dismayed by the unpublished bugs in Texas Instruments DSP, that was around 1999-2000, I thought that the FPGAs of the time had been grown big enough, namely the XC4013, to hold an entire eForth processor. Before that, I have been part of two ASIC developments which had a eForth processor in its heart, and so this was my third attempt in building a eForth processor. And I think in the remaining, 20 years, it got to a point that I'm very happy with it. And in a certain respect, what I did with the hardware development is very similar to what Chuck experienced in developing eForth in the first place. Because I used the different versions that evolved over time in all my projects since 2002, and eventually I came up with this version that I published on Git. So let's start. So microcore is a wildly, and you will see why this claim is correct, scalable dual-stack deterministic computing engine for real-time control. How do I do it? Okay. So the basic characteristics is it is a computing engine written in VHDL to be run in FPGAs. It is a dual stack design. Well, I don't have to explain this. It has a Howerd architecture. So the program memory is absolutely a different memory than the data memory. And the instructions are all 8-bit wide. And so the program memory is 8 bits wide. And the data memory is a different story. The word width of the data memory and the stacks is freely configurable. For practical reasons, the smallest microcore you would run is probably 12 bits, because then you can address 4096 memory program locations. And the upper limit is just the limitation that the FPGA imposes on you as far as resources is concerned. Microcore has a real postfix instruction set architecture. And in that respect, I would claim that this is the very first real eForth processor, because it also has the postfix mentality in its hardware. What does it mean? It just means that literal operands and addresses precede rather than follow instructions consuming them. That has a number of interesting ramifications. Microcore is a single cycle execution. It has no pipelining because I concentrated on getting the architecture right, and rather than running at the highest possible speed. Well, the speed is not bad anyways. It usually on the usual FPGAs runs at about 20 million force instructions per second. External events, there is, of course, microcore can handle interrupts, but it also has a second input, which is the pause input, which is inherited from the transputer, and I will go into more detail later. It has multiple data and return stack areas for efficient multitasking. The program execution is absolutely deterministic. And microcore is not only the VHDL code, but it is a complete hardware-software co-design environment and with its Forth cross-compiler. And Forth is actually microcore's assembler. There is nothing below Forth. So, and it has also a modelable instruction set. That means the VHDL code has been written in such a way that makes it easy to add instructions. The architecture. So that pretty much resembles the virtual machine of the Forth itself, but you see the clear separation. Do you see the cursor on the screen? Hello, feedback, please.
Yes, yes, yes.
Okay, so this part sort of is the Howerd 8-bit part, and the other parts are those parts that have the width of the data stack and the data memory. And the I/O registers are memory mapped, and the most important ones that are there a priori before any application-specific I/O registers get added is the status register, which is directly connected or very closely connected to the instruction decoder, the data stack pointer, the return stack pointer, the interrupt flags, the flags, all other flags that don't generate interrupts. It has a version register. It has a debug register that connects to the host via a two-wire umbilical link, and the debug register is the register on the microcore side that the host can send and receive instructions from. Then there is a timer that is also built closely into microcore, and also it has a special instruction and a control register that allows you to set single bits, plus all the registers that you need for your application, like A to D and input-output register or DAC output registers. So stack versus registers, I skip that, we know the stacks. My interesting result of analyzing the situation for non-Forth people is there are clear advantages of using a stack processor, and its big disadvantage is it is unfamiliar. The Howerd architecture, I talked about it. The instructions are all 8 bits wide. Data memory is independent, and microcore has no bytes. So the data width is the cell width of a memory location, and it has no concept of bytes. In retrospect, that has been a wrong decision because it clearly is contrary to acceptability of people who are used to more classical processors. The postfix instruction set. So it is the enabling technology for the configurable data widths. And what does it mean? There are 2 types of instructions in microcore. There are the opcodes, and the opcodes always have the most significant bit set to 0. And when the most significant bit is set to 1, we have a literal instruction, and the remaining 7 bits are the literal itself or a part of a larger literal. And you can build up a sequence of literals in order to construct numbers on the top of stack to a size or to a magnitude that you need. And in order to do this, there is a literal flagged register in the status register, which says whether the previous instruction had been a literal already or not. So if we have the lit flag bit not set and the MSB of the current instruction is also not set, then we have an opcode that does not need a literal. If the literal is not set and we have a literal instruction, that means that a literal instruction follows an opcode. And the least significant 7 bits of this literal instruction are pushed on the stack and sign extended. So with one literal instruction, you cover the number range of -64 through 63. And not only is the number pushed on the stack, but the lit flag is set. So if we go to the 4th case, we have the lit flag set and we have another literal instruction. Now, what is in now the literal the literal that up to now has been pushed on the stack gets shifted 7 positions to the left, and the new literal instruction is just appended in these vacated 7 positions. So if you repeat this several times, you can build literals of any magnitude. So with 2 lit instructions in sequence, you get from -8,000 to +8,000. And with 3, you already have, well, it's easy. It's 3 times 7 is 24-bit precision. If you push another one, you have 28-bit, and so on and so on. So you can construct any number of any magnitude without changing the instruction set. This is the important thing. And this is why this technique enables a configurable data width. So, and if we have the lit flag set and there is an opcode, then we have the situation that the opcode follows a literal. And if this opcode is a no-op, then by the no-op, the lit flag is reset, and we successfully have now a literal on the top of stack. And the lit flag, and by this opcode again, it's a 0, the lit flag is reset. So it is no longer, it can no longer be, let's call it augmented in its magnitude.
Do you have to follow literals with no ops, or could that just be an opcode?
No, that could just be an opcode, and even better than that, if it is, let's say, a branch or a call instruction, then if the lit flag is still set when you do the branch, then we are branching relative. So we add the PC to the number on the stack. If the lit flag is not set and you do a branch, then it does an absolute branch to the location, to the address on the stack. So, okay. Single cycle execution just means each instruction only needs 1 active clock transition. But microcore's instruction cycle may be several system clock periods long by way of a clock enable signal, which means you can run your design at 100 megahertz because that may be dictated by the application, but then you can execute only on every 5th or every fourth clock transition, you enable the enable signal, which means that then microcore has its natural, it is at its peak performance of between 20 and 25 megahertz or 40 nanosecond delay. That's what the microcore instructions take. So it can easily be integrated into environments. There is one exception to the each instruction needs one clock transition, and this is if you access the FPGA block RAMs. And the FPGA block RAMs, and I go back to the architecture picture, you see here an address register on the Prego memory. Well, that is unfortunately firmly built into the fabric of the FPGA's block RAMs. And more unfortunately, you cannot read out the address register. So in the first cycle, you have to set the address, and only in the next cycle, you can read the actual content of the memory. And this is why we sometimes need two instructions to do something, and they need to be uninterruptible. Because if I set the memory address and then get an interrupt, and the interrupt does something to the memory, then that is disaster. And to this end, there is a general mechanism in microcore that allows you to build multiple instructions that consist of multiple instructions, which are a sequence that is not interruptible. And that, for instance, leads to a plus store instruction that cannot be interrupted. And so it can be used to synchronize interrupts and foreground tasks. External events. Microcore has two different input signals to react to external events. For one thing, there is interrupts. We all know what that is. And I just spell this out. An event did happen that was not expected by the software. But then there is the flip side of the coin, which is the pause. And that means an event did not happen that was expected by the software. Like, for instance, if you want to fetch a character from a serial of a UART. And if nothing has been sent across the UART, then you cannot fetch anything. And so we all know what to do in the circumstance. There is usually a UART has a status register, and then you can probe a bit whether a character has arrived or not. Well, in microcore, you don't need to do that. You can just do a fetch on the UART register. And if there is no character, then a pause is raised, which in effect leads to the call of the scheduler and running a different task. And eventually you will come back to the task that experienced the pause. And at some point in time, the character will have actually arrived and the program can continue. This, by the way, is also something that I inherited from the transpooter, which, to my knowledge, is the first piece of hardware that had such a mechanism. As far as interrupts is concerned, each instruction of microcore is self-contained, and therefore microcore may be interrupted between any two instructions, with the exception of those that are, I call this chain, that are concatenated with each other. And all those instructions that exist are two-cycle instructions for various reasons. And it's about the pause. The pause is a mechanism that eventually allows you to do the resource management of, let's say, an A to D converter that is used by several tasks. you can do all this mutual exclusion and waiting for the conversion to be ready. You can delegate this to the hardware. And I think there is a transparency about this. So I talk about it later. The pause, oh yeah, here we go. The pause. So in a multitasking system, the pause trap allows to delegate, so to speak, the mutual exclusion of resources to the hardware. And then an 8-channel input, an ADC with an 8-channel input multiplexer can be controlled as follows. You store the channel number in the ADC. That starts the conversion. And then you just fetch the result of the conversion and store it in a variable. And ADC store will raise pause until the ADC is no longer in use. And ADC fetch will raise pause until conversion has finished. Hardware software co-design. The VHDL core for microcore runs on a target system. The microforce cross-compiler and debugger runs on a host PC. And it loads on top of GeForce 062, and because that is not very recent, Uli provided a Docker image for that. And it has to do with the fact that I needed to make changes to the a lot of changes to the interpreter of GeForce in order to efficiently implement the cross-compiler. And I needed to vector into words that nobody before ever thought that that would be necessary. So unfortunately, this in that respect is very hardware dependent. Then there is a two-wire umbilical link between the host and the target. An interactive force command line interface is mapped into a target. So you actually have the look and feel as if you would interactively program the force system on the target system. It has a disassembler. It has a single-step tracer, which is indispensable for stack checking, unless or until we finally have a fully functional stack checker. And both microcore itself and the microforce cross-compiler are based on the same architecture description file. And this is why I call this a co-design environment, because if you make a change to the architecture, not only does the VHDL code change, but also the cross-compiler changes accordingly. And to realize this, Microforce has a minimalistic VHDL interpreter that allows, it's mostly constants that have to be read by the cross-compiler. And so the minimalistic VHDL interpreter has to correctly interpret constant definitions of VHDL. Here is a picture of the total design flow. So we have the architecture description that I talked about. And on one side, it goes into the microcore VHDL code and the application-specific interfaces. On the other side, it feeds the force cross-compiler. And so we can do two things. We have a source code, we crank it through the cross-compiler, and then we can generate VHDL code that is the VHDL code of the program memory, and use this in a VHDL simulator, and on the other side is the VHDL source code that goes into the simulator, so you can simulate microcore executing force programs. So this is nice for development of new instructions and whatnot, or difficult interrupt situations. On the other hand, the cross-compiler can generate the binary, and the binary is loaded into the actual FPGA via the debugger. And this is also something that Uli has realized long ago. The FPGA is configured by throwing the VHDL code into the synthesizer and place and route programs. That is all standard technology. What do I mean by modular instruction set? Microcore has 47 what I call core instruction, then 24 extended ones, which are kind of a luxury, and 5 instructions for floating point, which means that there are 42 unused opcodes for application-specific instructions. And adding a new instruction is a 3-step procedure. So first, you define a binary code for the new opcode in the architecture package.vhdl file. On this way, the binary code gets communicated to the VHDL code and to the cross compiler. As a second step, you add a when clause in the instruction decoder's case statement. And that is all that is needed in order to define the semantics of an instruction. You find this case statement in the file mucontrol.vhd. And for instance, the code for swap is when op swap, then store the current toss in the NOS in the next cycle, and store the current NOS in the toss in the next cycle. So important is here the R dot and the R in dot. So R and R in are records that contain all the internal registers, and I can assign new values to R in, which will be transferred into the into the registers, which are here the R dot ones, on the next rising clock edge. And the third step is to define a name for the new op in the file opcodes.fs to make it known to microforce. And that's all that is needed. Instantiations. Microcore has been ported to Xilinx, Lattice, Altera, and Atle microsaming FPGAs. And in the development, I usually use a very small board with the LFXP2-8, which is not a very large FPGA, but here are some numbers. So if we have the core instruction set and the 16-bit word widths, we consume 988 slices. A slice in Lattice is 2 flip-flops and 3 or 4 input function generators. I'm not sure about 3 or 4. So we need 988, and I use up all the block RAM resources on the FPGA. So the data memory may be 6K wide and the program memory 8K. And the maximum clock of this setup is 33 megahertz. And which means in that instance, we have, so to speak, a single chip controller because there are no external RAM resources connected to the FPGA. It only runs from internal memory. So if we have the core and the extended word set, then we consume 1,199 slices, and it only runs at 30 megahertz. So if we have the core instruction set and a 27-bit word width, well, why 27 bits? At some point in time, it occurred to me that the block RAMs on the FPGAs are 9 bits wide and not 8 bits. And so why throw away the extra bit? And then you see the resource usage goes up. We only have 4K data memory because all of a sudden the data memory is 3 slices, 3 9-bit slices wide, whereas in the first case we only had 2 8-bit slices. So it's now only 4K, and the program memory always stays at that K. So core plus extended 27-bit is 1608 slices, extended and floating point and core is 1808. And if we only have the core instruction set with 32-bit, then we consume 1400 slices. And the data memory goes down to 3K. So, but as you can see, it is actually, you can set it to any data word width that is dictated by the application. And if you look at the human senses and what the maximum resolution of the human senses are, then you are fine with 24 bits. And plus, if you look at the technology, it is next to impossible to build an A to D converter, which is 24 bits. So a 20-bit architecture is what you actually usually need in order to solve your problems, and not 32-bit. And 22-bit is 24 plus 3 guard bits for rounding purposes. Additional topics. So these are topics I can speak about in the future, is the VHDL code and its structure, the microforce cross-compiler, which is microcore's assembler, the cooperative multitasker. That is a bit unusual. It is a cooperative multitasker as we all know it, but it also has prioritized tasks and round-robin tasks. And then I can talk about the pause mechanism and what you have to do the mutual exclusion in hardware. And what is also an interesting topic is floating point under the condition of a variable data word width. And I have some experiences and results there. Links. So microcore is available on Git. And here is its documentation, and the documentation means there is the microcore overview, which is basically what I have presented here now. Then there is an in-depth description of microcore, all the microcore instructions, an in-depth description of microforce, and the microcore public license, which is very similar to the BSD or LGPL licenses, which means you can use it and do with it whatever you like. But the license is special in that you are not allowed to claim that this is still the original microcore model. So this is a right I want to reserve to myself or to any licensed institution to take care of this. That's it. Thank you for your attention. Questions?
Thank you very much. Yeah, are there any questions? So please raise your hands or just open the mic and speak.
The microcore, what applications have you built it into that it's proven itself in?
Oh, quite a number. So the very first project I did was a seismic data logger that is used on the ocean bottom. Then a simple thing was a GPS to, there is an old standard for time synchronization, the name of which I don't remember right now. It takes a full minute to define the time, and it has long wave transmitters scattered around the world. That is a little bit outdated, but I once did a converter from GPS to this standard. The last project I have been doing was for the Merlin satellite a synchronization unit that conditions lasers to produce laser frequencies at a precision of 5 megahertz. And the application of this is that in hopefully 2025 or so, the Merlin satellite will be launched to measure the atmospheric content of CH4 of methane, right? Yes, at a precision of 150 by 150 meters by using two laser frequencies. So there are other.
I have a question.
Yeah.
So I have downloaded the microcore from the GitHub.
Yeah.
And here is a FPGA board.
There is what?
FPGA.
Yeah.
And I have a couple of other FPGA from the latest microcontroller from the Altera as well as from the other manufacturer, Xilinx. Can this be implemented on all of these?
Yeah, I have done that in the past. So I have written the VHDL code according to the 93 standard, because there are legacy development environments that don't allow, that have a synthesizer that doesn't support VHDL 2008. So yes, it should run, it should work. But one word of caution, you should get the latest version from GitHub, which I have uploaded only a week ago, because the version before has a really serious bug in it and wouldn't run if you only have internal memory. So get yourself the latest version.
Right.
Okay, got it.
Mm-hmm.
And once the fourth microcontroller MCU is created in the VHDL or Verilog on the FPGA.
I didn't understand your question.
I said, we have a FPGA, we have made a VHDL and implemented the core, microcore. After
Okay.
that, how we will program it with the Arduino IDE, can we be programmed?
Yeah, you connect it via, you have to set aside an input and output pin for the umbilical link, and then you have it under full control of the microforce development environment from the host computer.
Okay, that I understand. I'm asking about the IDE, integrated development environment.
Atar, now it's okay for you because we are 40 persons here in the meeting and everyone wants another.
I'm sorry.
Yeah. So I know Atle had a question, but Atta, you can just contact Klaus afterwards, and then you can discuss this. But Atle from Sweden, Norway. Yeah, sorry about that.
No, I was just wondering about those memory limitations. Is it possible to add memory chips and have access to them in case you need more memory?
Oh yes, there is provision for that. There is a general purpose external memory VHDL entity that is quite flexible. You can you specify how wide your word width you want is, and then you specify how wide the word width of your external memory is, and then all the rest goes automatically via this VHDL entity, because you may have to do several accesses to get the full data word width from external memory. Yeah, that is also already part of it.
Mm-hmm.
Excellent, thanks.
Okay. Yeah, I think, thank you very much, Klaus, and we are looking forward for the additional talks with the many interesting topics that you raised. So yeah.
Klaus, thank you very much.
Yeah, perhaps there could be some kind of voting somehow. Peter, you may be able to do that, of what is the most interesting topic for people.
Yeah, great.
Oh, a good idea.
Mm-hmm.
Excellent.
Yeah, we will do that. That's great. Okay, let's proceed. you can take an FPGA, but you can also grab a bunch of TTL chips and build your CPU from that. And that is what Andrew Holme will talk about. The TTL computer in eForth, second part. So we had a first recording and the first talk from you, Andrew. And we're very excited in how this concludes.
Can you hear me okay?
Yeah, we can hear you.
When Peter emailed me last weekend to say, was I ready to do the part 2? Could I do a demo? And the fourth computer, it's been in my loft for over 10 years since the last time I powered it up. And I thought it might be, should I wait until the demo to be the first powering for a bit of extra excitement? Ooh. But I decided not to do that. I have actually tested it, and it did work. And so I don't know if you've noticed, I've logged in from my work computer. I'm logged into the call twice because I wanted to try, and I'm going to demonstrate it to you on this. This is my personal computer, but I've got my work computer up here as well with a side view so that I can actually show you the fourth computer itself. Because the personal computer here, I need a docking station with RS-232. Nowadays, it's not easy to get a computer with Zoom and RS-232 anymore, of course, and it's not easy to turn it when it's on the docking station. So what I'm going to do is I'll switch over quickly to my work computer and just show you the physical computer, maybe just pull a card out, and then we'll come back to this machine and I'll share my desktop and just run a couple of demos. So if I just I'll just go onto the other computer for a second. I think I better mute this one, otherwise some weird things might happen. So I'll just go onto the other computer, and if I just
okay. Here we go.
Hopefully you can hear me and see me and everything again now.
Perfect.
Yeah. So here's the machine, which you may recognize. I thought, you know, I'll just pull what's the most interesting card, maybe the microcode sequencer. So there's the microcode sequencer with the ROM with the microcode in, and the old-fashioned wiring system that I started using. Maybe I'll show you a card with the newer pen wiring system as well. I'll just put that back in again. Yeah, later on, I started using the sort of Roadrunner. You probably can't see that well, you know, with the wiring combs system. And that's one of the index register cards.
Amazing.
I'll pop that back in. So here's the serial cable, which is connected to my personal laptop. And there's a bench supply here with 5 volts. It draws about ½ amp. So what I'll do is I'll go back to my personal laptop over here and share the desktop and run a couple of demos. Incidentally, we've got the Mark I fourth computer in here, but plugged into the backplane, but the Mark II cards are also stored in here, although not connected to the backplane. I mean, that would obviously be incompatible and short things horribly. There's no backplane slots at this end, but that's where those cards live. So let me just go back to the other computer and share the desktop. I'll leave the video of this one on, but I'll just mute it. Oh, I need to, let me have my speaker on, and then I can hear you. So hopefully you can hear me again now.
Yes.
So if I do share screen, that screen, there we are. And oh, do I need to get, oh, what's going on? I don't want, oh, what's it doing? Oh, I don't want the zoom thing in the screen. Oh, let me do stop share. I'll just go out, I want to get out of full screen mode. How do I do that? Oh, finally it's done it. Okay, right. So now we'll do share screen. That one, share. Right. Hopefully you can see that. Let me get rid of this little bar here. Okay. So can you see my screen? Okay.
Yes.
Right. So I've got hyperterminal here. So I'll run that. So what I'm going to do now is just switch on the bench supply. Oh, it already, oh shit, it already was on. Ooh, and I pulled cards. Oh, that was a bit dangerous, but it works. So, I mean, a very quick test would be, you know, there we are. But I'll just I've got some slightly more interesting demos that I can download over the serial port. So I'll close hyperterminal. And if I just run this, it's a little C program that just sends the characters and waits for the echo at the end of the line, you know, to pace it. If I run that, there's a little VList routine. Now, the next thing, who can guess what this is, or who might recognize it? I'm showing the book to my other laptop. Is that on my other laptop? You might be able to see my extremely thumbed copy of Thinking Forth, because that's Leo Brody's sort of do a make example there. And we've got a little hex dump thing here. So that's finished downloading. So we'll go back to hyperterminal now. But what I've downloaded there, I don't know if you can read that. I've got a little VList and then Leo Brody's Fig model of do a make with the demo, and then I've got a little hex dump at the bottom. So back into hyperterminal. And still alive. So if we run the VList that I've just downloaded, you've got a pretty standard looking Figforth VList, but you can see the extra words at the top there that I've just downloaded. So for instance, I've got this little hex dump. If I go 0 dump, that's the bottom of memory. That FF there, that's the interrupt vector, which I'm not using. And then the 400 hex is the cold start, the reset vector, which is pointing at address 4, which is the next byte. And then 0152 is the CFA of the UART initialize routine. And OB82 is the CFA of cold start. And I should be able to prove that by saying OB82 CFA to PFA, PFA to NFA, ID dot is cold. We can run the Leo Brody's do a make demo as well. You just say recital, and it says your daddy is standing on the table, ask him why. You all must have seen this in the book at some point. So you go why to change the light bulb, why because it's burned out, why because it was old, why because we put it in there a long time ago, why, and so it goes on. and you see the speed of the machine. It's very similar to what Forth is like, the feel of Figforth on an 8-bit microprocessor. I mean, the things running at a megahertz, and you've got the two levels of machine. You've got the sort of micro machine, microcode, with an 8-bit data path, and then the Forth virtual machine on top of that. And I do have this diagram, which I think we looked at last time, of the virtual machine which the hardware implements. So in hardware, we've got the standard Forth registers, the W, the IP, stack pointers, and we've got 16-bit addresses. It's a 16-bit Forth, but to make the hardware simpler, the data path is 8-bit, and data moves around 8 bits at a time. So it's very similar in the feel of it and the speed of it, to an Forth on an 8-bit microprocessor. I'm looking at the time. I can go on. I can talk a little bit about, in more detail. We can have a very quick look at.
Go on. No
Please
problem.
proceed.
We'll go a little bit further on then. So the microcode. Here's just a little example of what the low-level microcode looks like that executes on the hardware using the registers of the virtual machine. This is at the top, you've got the reset vector, the entry point. You remember when we did that hex dump, we saw the interrupt vector and then FFFF, and then we saw the reset vector at address 2. And that's what this code does here, is it moves 0 into the W register and increments it twice to get the address of 2, which is the reset vector. And then it disables interrupts, and then it moves the 16-bit reset vector 8 bits at a time into the IP register, IP low and IP high. So the instruction point at IP is now pointing at the compiled Forth code, which you remember it was UART init followed by cold, and then it drops through into our old friend next, and this is the Mark 1 Forth computer's next routine, which of course it's all about how fast your next is, isn't it? And this one is 1, 2, 3, 4, 5, 6, 7, 8 instructions, so it's running at 1 megahertz. If we were to ditch the interrupt, which I don't use, we could get that down to 7. The way this works is it takes the instruction point, it fetches the instruction pointer, loads it into the W register, and then the W register is now pointing at the CFA of the word of a word, and I load that into the op register, because the way the architecture works is that the CFA contains the micro instructions, which are I can show you some examples in a minute. The things that would be written in assembler, on a 65024 Forth, the code words on this machine are written in that microcode on the microcode sequencer we looked like. So anyway, this loads the CFA, which is a micro instruction, into the op register, and then it does XOP, which basically is like a sort of an indirect jump on the micro machine running that opcode. So I could show you back on this diagram here. Here's the op register that we're loading. We're loading instruction CFA, which is a micro instruction, into op, and then that gets loaded into the program counter of the micro machine. And there are a few at the beginning down here. We've got enter, exit, and literal. Enter decrements the return stack pointer, moves IP onto the return stack, copies W into IP, and then does jump to next. So, you know, it's all standard low-level fourth machine stuff. And a literal decrements the parameter stack pointer to make some space, and then moves the IP is now pointing at the next word in the compiled code, which will be the word following lit. So we move that to top of stack low, increment IP, move IP to top of stack high, increment IP, and jump to next. I've also got here the beginning of what I call the macro machine ROM, which is the one where all the high level code is. And, you know, as is customary, I made it with a standard assembler. So, and I used, showing it to the other camera, I've got here my installation. Oh, it's probably not. I've got Bill Ragsdale's installation manual from November 1980 for 6502 Forth, which I used as a template to create this version. Here's the reset vector here, and this is the bit that we did the hex dump of. There's the UART init pointer followed by the cold pointer, which is the two, you know, we were looking at. Here's a little macro that I use for building headers of words in the dictionary. One little deviation from the standard Fig model here is that my dictionary is a doubly linked list. So rather, because standard Fig Forth has that traverse word that allows you to go backwards and forwards over variable length name fields, rather than doing that, in the LFA here, I've got two pointers. I've got the link pointer, which is the sort of forward pointer to the next word, but I've also got the NFA pointing backwards to my NFA, so that I can do the equivalent of traverse, you know, without actually scanning. Another small deviation from the Fig model is that my CFA is only 1 byte, because it's just an opcode for the micro machine rather than a 16-bit pointer to code. And actually, I've had second thoughts about that since that, for, you know, achieving sort of total compatibility with the Forth model, if I was doing this again, I would probably actually make the CFA 2 bytes, even though the second one would always be 0, because, well, just to make it more standard, really. Because if you probably won't be able to see this, but if we look at in this code here, CFA to PFA I've got here for the do and make example requires CFA to PFA 1+, whereas it would normally be 2+ in a standard Fig model. And for the sake of wasting that byte, I think if I was doing it again, that's what I would do. So just a bit more. I'm nearly finished, but here's all the low-level microcode words that are defined with using the macros. So it just creates a dictionary entry with a CFA that is the opcode basically, and it's the standard set of low-level words. And then finally, I've just got a few examples of high-level words, the terminal IO functions, the way that they're defined, with the equivalent Forth on the right-hand side. You know, for instance, emit, you've got the address of the UART output buffer, cpling, and then we've got a little begin until loop waiting for the, you know, transmit register empty flag. And yeah, and basically, you know, the procedure was to go through Bill's installation manual for the 6502 and translate it into this kind of thing for the Mark 1. And I guess that's probably my time allocation. So perhaps we'll leave it there.
All right. Wow. Thank you very much.
Awesome. Absolutely awesome.
And I'm sure there are questions. Wow, that's amazing. So are there any questions? Raise your hands, open the mic.
Hey, Andrew, I was just curious about your chassis. Is that a homemade or is it off-the-shelf chassis you found?
It's a standard IEC DIN rack with standard Euro cards and standard DIN connectors that I used. And then, as I say, I initially started out with using Kymar wire bunch, rather untidily routing it around the chips. And then I switched over to using a pen wiring system with the
nice.
rat race guides, comb guides.
Thank you. Good job.
Hi, can I ask a question? I don't know for the people.
Sure.
I can only see about 6 people in the list. I think obviously you're really quite pleased later on in your web page about how other people. There's another guy who took up to replicate your Mark 1 4th computer, and I keep thinking, you know, what kind of effort and whether it would be worthwhile from your viewpoint to create, say, a proper PCB version of the Mark 1 4th computer so that other people could actually build their own TTL computer in a similar manner to, say, how the RC 2014 Z80 based systems have become really quite popular, because it does convey a sort of like a real understanding at a TTL level of how a real computer can work, and it is really quite minimalist and yet completely functional. So what are your thoughts on sort of being able to propagate this a bit further for the people?
Yeah, well, it's an interesting point that you know, you may have noticed at the bottom of my web page, I'm in this web ring called the Homebrew CPU web ring, and originally, you know, sort of 20 years ago, when am I muted on this one? Oh no.
No,
It's
fine.
No, sorry, the video went to the other one. That was weird. On that web ring, there was originally like 4 or 5 projects. Like there's mine, Bill Busby's Magic One, which you might have seen, and a couple of others. Yeah. If you go to that web ring now, there's about 20 or 30 homemade computer projects, all unique designs that people have done. And it's obviously, it's something, making your own computer out of TTL is obviously something that appeals to people. But to make, I mean, that's probably a PCB, a single PCB, to make the Mark 1 more replicable. It could be made a lot easier. I mean, that Malaysian student did a really good job to copy it. I mean, some of the diagrams are a bit pixelated and ropey, and you know, I think I had to send him hand drawings of the diode ROM because it wasn't properly documented, and he did a really good job of doing it, and he got it all working. You know, he sent me his dissertation. Yeah, but and one of his fellow students replicated Bill Busby's Magic One, by the way, which is a much more serious undertaking. But yeah, I could think.
But it doesn't have 4th, does it? It doesn't have 4th. Magic One doesn't have 4th.
No, it doesn't.
You only got Minix on it, so
yeah.
Okay, are there any other questions? Well, Julian, then that's the perfect introduction for yourself, because you're the next speaker, and we will hear a follow-up on Fignition and what the flash transition layer is about.
Oh yeah, that sounds good. Yeah.
Go ahead.
Okay, I'll
Please.
try and share it. So I'm sharing. Here we go. So you should be able to see Keynote, and okay, it started. So here we go. Yeah. So this is VDisk, a flash translation layer in eForth for Fignition, and I'm Julian Skidmore. I got the usual stuff. And okay, so part of the introduction is like this. Sometimes it takes a long time to write software you always wanted to. So let's recap a bit. Fignition is a self-contained fourth computer inspired by the Jupiter Ace and also Andrew Holme's Mark I fourth computer, which we've just seen in action. It's intended to be the simplest complete self-hosted computer I could design, simple enough to be fully understood by a single person and soldered together by a child. It has an AVR MCU which manages the devices it talks to, a fourth compiler, a keypad for typing programs, composite video out, USB for power, 8 kilobytes of RAM for the current user program, and half a megabyte or a megabyte of flash storage, because no one could ever need more than that. So today I would like to talk about flash storage, which implements a flash translation layer with garbage collection and wear leveling. But first, a bit of history. So I used to work for a company called Microcontrol Systems way back in 1992, and it was my first full-time embedded computing job. And what we did was we developed things like 6 megabytes. This isn't actually one of the cards, I couldn't find it. 6 megabytes solid state ISA cards for PCs, which pretended to be hard disks using a BIOS extension. So they could be RAM or EPROM or the very latest in non-volatile storage, 128 KB flash chips by Intel, which had one whole flash sector on them. Okay, the flash memory then was like the flash memory now, but a bit more crude. You know, you could electrically erase all of it to ones, and you could write individual bits to 0. But our system only allowed customers to write to the disk once. And we did that by putting the FAT and the directories and caching them in the PC's RAM, and then the customer would copy all the files, and then they would get copied back onto the flash memory. So I was nearly fresh out of university and realized we could make a proper solid state disk using flash with the right data structures, and that would be brilliant because there were literally no standards for true flash based solid state storage. If we had solved it, we could have defined the standard, and together we could have ruled the galaxy. But the company wasn't interested, and within a few years it basically went bust. It took 20 years and several design attempts later to develop my own flash translation layer, as they're called now, and it turns out we can develop simple ones in about 1 to 2 kilobytes of code, which is similar to a floppy drive controller. So let's look at the flash memory. SPI flash memory is random access. All we need to do is send a read or write or erase command followed by a 24-bit address, and then we can start writing or reading at that location. Although you can read from anywhere, you have to write from the beginning of a 256-byte page, and you can only erase from the beginning of a 4 kilobyte sector. In flash memory, erasing always sets the entire sector to 1 bits, and writing can only ever reset bits within a page to 0. However, on most flash memory controllers, you can do this multiple times. You can clear more and more bits anywhere within the page each time. And this means we can't treat flash like an old-fashioned disk. We can't overwrite a page with any new data we like. We normally have to write to a new page containing all ones each time. So what we want to do, if we want to have like a proper flash type disk is that we need like virtual blocks. We could map our logical or virtual blocks to actual physical pages we wrote to. And the easiest way to do that is to build a virtual block table. As we update the virtual block table, we would update its entry point to the new physical block used. So for example, in this case, in the virtual block table, at the very end, we have virtual block 4, okay, but it's really pointing to physical block number 7, okay, and we can see that, for example, earlier on, physical page 0 have been replaced by another block earlier, so it's no longer in use, okay. But the thing is that,
excuse me, I'm still looking at the first presentation page. Is that just me, or is?
Can no one see any of this? Is it just me talking and no?
It's just the first page, yeah. Oops.
Thank you, Keynote. I thought I was sharing.
So we see the presentation view of Keynote with the slides on the left and the first slide in the middle.
Okay, so you can see where it says updating virtual blocks now.
No, it's just.
You only see the first slide. Yes, you don't see any of the others.
Yeah,
the first slide only.
The first slide on the list of slides, thumbnails.
Resume share. Okay. It says resume share. So you can't see anything. You can't see any of me changing anything.
We could see the first slide, and I think.
I thought all that was the prelude.
That's what I'm
Can you see anything at all changing on the slides?
No. What? So why don't you stop sharing and reshare, and then we see if it works then?
Right. Okay. I'm really sorry about that.
Something bad happened when you pressed play, I guess.
Oh yeah, maybe it's a different window. Okay, right. Share screen. Okay. Right, does that work?
We have first slide full screen. Great.
Okay, can you see the blank?
Yep.
Screen? And now you can see Fignition.
All right.
Fignition, awesome. The printed circuit board populated.
Right.
Yep.
Okay, so I think I'll have to go back to that, and I'm sorry about just having to look at the original screen all that time. So, Fignition, self-contained computer. And what happens is that we know it's derived from this, and we know it's derived from the Mark 1/4 computer. Kids have made it. They were really happy when they made it. And we see that Fignition is self-contained. It does all the things that you need. I used to work at Microcontrol Systems. We made 16-bit ISA cards, but they didn't really look like that. They were full of memory chips. And one of the things that we used to use was flash memory chips, which was quite new. And I wanted to be able to write some software that would make it a proper flash disk instead of just this kind of rudimentary system that you could only write once to. So serial flash memory is organized. You can access it randomly anywhere, but you can only write in 256-byte pages on AMIC serial flash memory, and 8 pages of those go together to make a 4 kilobyte sector, and that is the level at which you can erase it back to ones. And when you write to it, all you can ever do is 0 the memory. So what we would like to do, because we end up having to use the new pages each time we want to write to some memory, we would like to be able to have like virtual memory blocks where we say we're like writing to page 3, and it allocates a new physical block to write to. So we can have a virtual page table, and as we update oh, there we go, that's how it works. That's how it starts off. And then we want to write to block 4 again, and this time we have to use page 7 because that was the one that was next available. Oh, that's good, nice bit of animation. And so the thing is that we can't actually store the virtual block table in the flash itself, because that would involve changing the contents of the virtual block table, which you can't do for the same reason that you can't arbitrarily modify flash pages themselves. So what you note, though, is that every time you have a physical page, then you're going to write it, you're going to write the virtual table entry into the next physical page. So you could in fact represent an inverse virtual block table so that each new element in that page represented the virtual block you were writing to in the new physical page. And from that, you could reconstruct the virtual block table that you want. And in this case, physical page 0 originally contained virtual block 2, physical page 1 originally contained virtual block 3, then physical page 2 contained virtual block 1, but later that was overwritten later on with physical page 5, and so forth, so forth. Some of these pages get overwritten, and in our case, as before, the physical page 7 now represents virtual block 4. So this means that because what we want to do is the data about the virtual page table represents metadata in addition to the actual flash storage that we need. So we represent it in a different location. Okay, so as we modify Flashbox, the content area will get filled up. So what happens when we run out of flash? Okay, and the answer is we perform some garbage collection. And garbage collection works like this. So if we imagine that this is a section of the flash memory and some of these blocks are clean because they are still blue, and some of them have been overwritten and they are dirty blocks. And that happens all the way, say, to the end of the flash memory. So the algorithm waits until we've only got 8 free pages left. And then what it does is it goes to the very first page that we started to write, very first sector that we started to write to, and we copy over all the pages that are in fact clean. And this leaves a few, in this case, pages 2, 3, and physical pages 2, 3, and 5, which have been overwritten later. So then we have 3 free left, and then we erase the first sector so that we can then carry on writing to the flash memory. And what happens there is that as we do this, we continue to fill up the inverse virtual block table with new physical pages that we have written. So eventually what happens is that the inverse virtual block table will fill up too. But garbage collecting for that is much simpler. All we do for that is that we have 2 tables. So the first table is allowed to be filled up, and then it gets to the end, and then the second table, we allow that to fill up. And when we've got to the end of the second table, we know that all the physical blocks that were used in the first table will have been substituted with the physical blocks in the second table. And therefore, we can just erase the first table without having to be worried about whether we're losing any data whatsoever. And this is the summary of how it works. We start off with both tables not overwritten at all. Then table 0 starts to fill up, and then table 0 is full up, and we start to fill up table 1, and that eventually gets full up. And we can erase table 0, and then once table 1 has filled up completely, we can go back onto updating physical page entries on table 0 and erase table 1. And there we go, a complete algorithm. So the firmware itself for this algorithm can actually be put, I can put it on the whole screen. You can, it's quite tiny, but actually it's relatively short. It's about 300 lines of mostly Forth code as it appears in the Fignition GitHub. It's not quite standard Forth because it's sort of got various sort of quirks that allow me to compile it into ROM, but it wouldn't take much effort to convert this into something that was a standard forth. So, summary. VDisk shows how simple a flash translation layer can be, and was the fulfillment of a project I wanted to do for the first company I worked for 20 years earlier. So thanks for listening to this. Does anyone have any questions?
Thank you. Thank you, Julian.
Oh, other questions? Please raise your hands or open your mic.
Oh, I'm so thankful that somebody told me that it wasn't really working correctly. I'm really grateful that I was able to correct that. Thank you.
Is the wear leveling handled as a higher level function, or is that part of the part of your stuff?
It's just an inherent property of the simplicity and the crudity of how the flash translation works, because I just end up writing to the very end of the flash sectors and then wrapping back round to the beginning. All the flash sectors get written over at the same rate, so it does wear leveling as a byproduct of that. More sophisticated flash disks, what they do is they wouldn't do it quite like I would, because it gets inefficient searching through all of the long list. I've just got a linear list. So what they do is they break up the flash disk into smaller parts and try to balance the number of writes on each part. Because if, say, what typically happens is that certain parts of the disk will get written more often than other parts, so they have to balance it. But in my case, it's just a simple property of how the algorithm works.
Thank you.
All right. Are there additional questions? Doesn't seem to be the case, so thank you again. I really appreciate that. And yeah, mass storage important also on small devices. Yeah. Right. So we proceed, and our next speaker will be Thomas Goeppel. Hello, Thomas, and he will talk about MODBUS Server with the STM8 eForth, a modular one, and I'm very curious how this looks like. So, Thomas, are you ready?
First unmute, then camera, and now where was that screen sharing option again? Here. Okay.
Yep, you made it. Yeah, we see it.
Okay, cool. So now I prepared a couple of things here. First, yes, this is about a modular MODBUS with STM8 eForth. So first, what's that STM8 eForth? STM8 eForth is a very small forth system based on eForth that is optimized for a very tiny microcontroller. So let me just show how tiny this thing is by today's standards. So it's a budget microcontroller based loosely on the 6800 architecture. And it's just, well, a few bits short of the 6809. It's like the idiot of the family. So it has 16-bit capabilities, but just enough to wish you had more. And it has a very nice feature that is flash memory. So it's a self-contained system, and it can, and this is the main thing, it can use flash just like RAM. And this is like the dream come true for someone designing a small system that's self-contained, that actually works like a microcontroller-based force or microprocessor-based force of all. The MODBUS uses, it's a little bit lagging here, So it can be used, for instance, for a microcontroller board like this one. Is a very cheap board from China. It's a standard thing, €6, €7, even now on Chip Crunch, still picking ahead at that price. This board normally has a MODBUS stack. It can also be applied to anything else, like with an STM8 microcontroller, like this tiny one here with just 8 pins. So I made this board that fits in a 7mm diameter tube. So the implementation that's provided here is a complete minimal MODBUS set. MODBUS is a field bus system that was designed, I think, in the 80s or beginning of the 90s for industrial automation tasks. And it's still very popular because it's so basic. And here we're using the RTU protocol. That's a serial line protocol. Most Modbus devices today use Ethernet, but for home automation, that's still very interesting because you can use a cheap RS485 connection and have your AO nodes. So this is the code that's already in this repository. But the interesting thing, it's actually modular. So what we have here is a software stack that consists first of STM8 eForth, which acts as a kind of very small operating system. Then we have a layer of hardware abstraction bus control for controlling the direction of communication for the Modbus. Then there's a UART, ISR, what else? And then the thing that's called MB Proto. That's actually the complete Modbus protocol layer. And then you can put any kind of server on top of that. I will demonstrate that right away. So first, we go directly to the demo, because it's more interesting in looking at web pages. So this is this device. Here's the camera. That should be live. It's live. So we are going to transfer STM8 eForth to that board. So now it's compiled, it's transferred, and there it is. Now we have STM8 eForth on the board. We start eForth.com. That's the normal development environment for this small board. We are connected here through that link that's at the same time the programming link for downloading the core and for serial communication. So the serial communication is actually full duplex communication, not through the UART, but implemented in software. So we have a standard word set of eForth. It was used for usability, but the other words are still there. They're just not linked. That's one of the particular properties of STM8 eForth, that you can use alias words and have headless words in the memory and load the words as you need them, link them up as you need them. So now we'll load this program that will load the basis for the Modbus communication, the complete protocol. So it takes a little time, not too much. It's actually much faster than what we saw in this TTL computer. But it's still taking time. I think the PC is currently heavily loaded with Zoom. Now, from the 8K flash, we still have 2,000 bytes left. So 2Ks are left. But we have a complete stack in there. So now we load the rest of this Modbus thing. That is for the demo. That's the name of the board. Of course. So it shouldn't take too long. That's assembler, CRC functions and whatnot. So here's the rest of these function codes that these instructions you normally set through Modbus. And here we are. So I already set that up here. If I send now, there should be maybe an error. Here it is. So now it works. After there are some bugs on this QMod master. So if you ever work with that, you have to be patient. But it's certainly better than nothing. I use this to be sure that other users, and there's quite some, have a testing environment. So now you see the LEDs are off again. I can turn them on again. So this would be the function code for setting a group of outputs that would be realized in that case. So there are other function codes that are all implemented here, like setting holding registers. Why are they called holding registers? I think that's because this Modbus was invented by a Swiss company, and holding Halteregister, that was German. Actually, it is a Germanism. But there are a lot of details you can see in the documentation if you're ever interested in Modbus reverse engineering. That was interesting. So this is now a standard Modbus node that anyone can use for automation. But that's not why it's so interesting. So nobody would need a layered thing for that. Let's wipe it again. So I made sure that the protocol layer is still in there. And now I load something that's a little bit more interesting. That's just a demo for these register settings. It's very short. So we still have 1.7K left. So a lot of things would still fit in there. And this is interactive. So maybe a few words about why this is. Okay, let's try that. So here we go. There's non-initialized. We got one value, register value we can set in. I can transfer that again. And you see that here this thing, my register, is currently active. So what is this code? We have just a simple handler for the one Modbus command. So register right, and link that up here for this word with the decoder table of the Modbus protocol. That means that essentially you have everything wired up to implement just the handlers that you need. So it can be setting outputs, can be reading registers, can be writing registers. It's really easy to do that. Here in this thing.
Okay, mal weggehen.
Sorry. Okay. Initialization of the thing also wires up a default action handler, and it gives us this dump thing where we show see the output. We can silence the dump very easily because that's just a function handler here. If I say 0 MB so now it should be silenced and only gives us here this message which register was written. So this is still not the most interesting thing. We can add very easily more functions to that. So I prepared a small demo for IR control. You see this LED here is an IR LED. So great. Let me check that. That's annoying. Oh, yeah. Not good. It should work. Ah, yes, okay. That's of course because the one wire is missing. Yes, okay, cool. Look, good. So now we have an IR control, and it's quite easy now to use that through MODBUS. So all I need to do is use that demo handler I prepared and write that to the action handler. Cool. So now this code here would be then, of course, the IR code. Look. Works. Okay, it was a little bit of magic around this very small stack. If you're interested, the source code is of course on GitHub. The IR controller is also a little bit of code I cooked up for this microcontroller. It's here. So it's for one of the standard China light bulbs with IR control for a couple of bucks. Here's the table of these codes. You could also do a lot of other things with that board, like implement, let's say, some heat controller or some water reservoir level controller. A friend of mine implemented automation for his boat using that. So here is for water conditioning a MODBUS node that does its own stuff, that has its own controller, that is very resilient, that's otherwise connected to Raspberry Pi, and allows controlling that boat also from at home. That was it. Questions?
Thank you very much.
Amazing, fantastic.
So, are there questions?
No questions.
No questions. So, overwhelmed.
Thomas, I use the MODBUS very much, but I really don't have questions. I would like to try it first.
Sure, sure. Thomas, can you put the link in the chat for your GitHub repository? I think that would be fine.
I had a MODBUS question. It may not be so much a fourth question, but is the communication reliable for errors? You know, if there was a bit flip or
well, okay. So
error.
This MODBUS RTU, of course, that's a very old thing, isn't it? It has a 16-bit CRC. How good is that? Well, it was good enough for most applications, but personally, important things I would send frequently and make sure that the repetition rate is shorter than the maximum allowable failure time.
Thank you.
Just to make sure that you do not miss anything. And I would also implement additional safety features if it really would be necessary. So it's reliable, yes. It's been used for industrial automation a lot, but, well, you know, 90s technology.
Right. Yeah, Thomas, thank you very much. And I can encourage everyone to have a look at Thomas' GitHub pages so that you can see how what famous work he did on STM8 eForth. So that's really amazing. Not just the MODBUS server, but all the rest. Really, really nice to see. Right, we come to our next speaker, and that is Atle from Norway, as I learned. And he's talking about ESP32 Superexpander. I don't even know what that would be, and so I'm very curious to hear about the explanation. Atle.
Okay, well, I'm an old programmer, an old Java programmer, so that's where I come from. Then I got, actually my wife bought me a little robot. And so I started out with this one, trying to connect everything. I tried to connect everything to these pin headers here, and then I realized I needed some kind of card to put it all together. So I made a little card to put it together, and then I was wondering, is it possible to make that as a PCB? So I made this one, and I even put some LEDs there, and I broke out the I2C bus and a bus for these time of flight sensors. Now that's a few months ago, and that's when I got the idea for this thing, and I'm going to show it here first, just so you get a feel for it. So it has counters to keep track of how the wheels move, how far each wheel moves. That will send pulses that will be stored in these counters, and there's I/O, a lot of serial to parallel and parallel to serial registers, and some of it I've broken out, or I've connected one of these registers to the inputs of a motor controller, and I have all the stuff that I used to have. I've broken out the I2C bus, I've broken out a serial bus, etc. And that's the hardware part of it. I want to have sensors all around here. You see, I've already mounted some sensors to the front here. And now I'm starting to program this in eForth. And now I will try to share a portion of my very big screen. And that worked when I tried it the last time, so let's just cross our fingers. Do you see two half screens and this Fortmobile? Do you see it?
Yes.
Excellent. All right, let me see if I can. I had a better view. Here you see the motor controller, and here you see some of the LEDs. I'll turn it backwards so you can see the whole board like this. That gives you a complete view of everything. And now I will just show you some of the code, because everything here is coded in eForth. The motor control, the registers, everything. There is no C code added to the ESP32 eForth that is running on this. So how I read it. Here is how I read the inputs. So I read them into three different registers. that means that I get 8 1-bit inputs and the 2 counter values. And then I can also write something. I saw those beautiful relays, and I regret not having hooked up these, because they would give nice clicking sounds when I show the outputs later. But anyway, that's how it is. Then for example, to control the motor controller, to set it to go either forwards and backwards, I need to flip 2 bits for forwards, and then I need to flip 2 other bits for backwards. And this is how this is done. I have the out register, and to go forward, I set these bits and I zero those 2 bits, and I send that to wait, and I and in, of course, I clear all the bits except those 2, and then here I clear all the bits except those 2. Do you see all this? Yeah. Then in order to update the registers on the board, I have to write the contents, and that's the procedure. That's the word that you saw up there. So now let's do some fun with it. Let's see if we can drive. Yes, we can. So now we are, perhaps I should move this up. Do you see it driving now? Yeah. Okay. So now let's go off course a little bit. Do you see me turning the wheel? Let's see. Maybe I should, yeah. Now we're on course because I've adjusted. So this this thing here would be correcting the course and increasing or decreasing the speed of each wheel as it was driving, of course. Now, if we're drifting left, then we have to increase the speed on the other one to get back on course. Then if we get close to an obstacle, then we're backing up, and that happens. You should be able to see it here. Let me see. Now we're colliding, and it should be red here, and now it should be green, and then it should go red. That's one thing, and then I have since, hold on, I can't get back into it now. Oh yeah, okay. And since this is for newbies having fun, then I have a little humor thing in here as well, because I was wondering if this was maybe getting sentient. high impedance, of course. And that's basically all I had. The next thing to do for me now is to put it all together and perhaps put Raspberry Pi on top here, because I just had this idea that if I could describe, to control this and set the course for it, here I call the course a derivative, because the course, if I was able to describe the road as a function with some curve fitting, for example, if I'm to avoid an obstacle, I could describe a half circle, and then I could follow the derivative of that function, something like that. That would be what would be coming next as soon as I get this finished. And that's what I have.
Okay, cool.
Like that? Good, excellent. I'm happy.
Amazing, fantastic.
Thank you very much. So that's really hands-on. Yeah, and we see it live and moving. Great, thank you very much. Are there any questions to Atle or hints, recommendations? Raise your hand.
Yeah, absolutely. Recommendations, things, ideas. I mean, counsel, advice.
Mm-hmm.
Atle, you have a very good wife. I wish I had, my wife bought me robots.
Yeah, she's the best.
Right. Well, maybe later on, or you know how to contact Atle. So
yeah, everything is on GitHub. All the design for the board, all the source code, everything. I'll put that GitHub reference in here as well.
Yeah, great. And then people will be able to contact you afterwards as well. So that's great.
Yes, and the IDE, of course, is also on GitHub, the one that I was using to load and edit all this code.
Right. So if there are no further questions, then I would say we come to our next speaker, which is Peter. And Peter will talk about ESP32 force as well, and how to connect it to a TFT touch display. Peter, please go ahead.
Excellent. Here I'm coming. So
yeah, we see that.
This is the terminal. This is my terminal. This is my my video, my second video, and here you see me trying to work with this. One moment. So I clear my screen. You see the screen. This is a live, and you see here the ESP32 and the display. So I created some words to control this TFT with ESP32 force. And if you want to follow this project, you enter into this ESP32force.org from the Force 2020 org, and you go to project number 16. This is the ELI 9488, which is a 3.5 touch screen. You have a lot of information on this page, and you have the GitHub link, and you can download the documents how to wire this this screen. It's everything here on this GitHub. And of course, you enter over our site for 2020. There is also a link here on blog. So I want to show you a little bit of some of the code I was testing. So for example, we are going to see a calculator. I'm working on a calculator. And you see, I need to find my stylus.
Wow.
I can hear pressing the different let me adjust the camera. And of course, since this is force, I am not really trying to make a calculator because this would be too easy. I have a lot of menus here, and this TFT screen, I am trying to use as a remote control for a Ford mobile like Atle has, and for other things. I want to use it as an intelligent remote control. But also, I have here, for example, a servo motor attached to the ESP32. So I want to show this motor here. Sorry for the camera, this is very complicated. I have a lot of cables here. And I try to open this a little bit more. So you will see, I will control the servo on real time using my commands are here. I had to disable my mouse and I am a bit lost here with there's so much USB connected to the computer in a moment. Oh, here. Everything of these programs are on the solid disk, on the block file disk. So words and here are my programs. This is my part, my user words, and these are the system words. I separate this with the line here, as you can see. So there is a lot of code here, and some of them you will see here 99. It's this one, this pot servo. I will steer a servo with the with this. This is one of the words, and I will do menu. So I got the menu on the right of the TFT, and I will add a pot servo. This is this one. So I can steer a servo, you see. This is the servo moving here in the back. I can do clear screen. I have, for example, other graphics here to show you. A calculator, again, and the potentiometer here. So this is really interesting because you have a lot of possibilities to show information inside the ESP32. And for example, I have here a temperature sensor, and you can show everything on the graphics display as also on the Wi-Fi, because you can control this. We are working with Brad will show us later. He recovered the Telnet. We had a problem with Telnet. Now it's working again. I was experimenting with Telnet. It's very nice, really interesting. And what else? Well, this is a work in progress, so I will continue showing you in the next meetings when we have something new. As you can see, there is a lot. Here is a lot of work in this little demos, but these demos are 30 screen long. You see here, this is to create a potentiometer with the menu. Here's the potentiometer and the ball and the buttons. Here are the buttons defined. And I will advance with this, making full GUI. So I want to make everything on graphics here, because it's very easy to program after you have this. Of course, you need the skeleton, and you need to write the skeleton. I will share with all of you on the GitHub, on my GitHub. But after you have these words defined, you can work with we have, for example, triangles. This is a full graphics process. So you have triangles, you have rectangles, you have colors, a lot of palettes of colors, and well, you can do what you want with this. This is a small computer. One of my ideas is to solder one of the ESP32 right back on the board here on this. What is my video? I showed this on the last meeting. I think we were talking about the screens. It was not recorded, but in the back of these boards, you have the SD card. So you can work with the SD card. My idea was to solder directly the ESP32 over here, to have a smaller, to get a smaller. Now I have these long cables, but you can buy now. There are some manufacturers selling this kind of displays, but here in Brazil it's very expensive to get one of them, and so I will try to make my own soldering just with the in the back, the ESP32. But there are limitless possibilities. You can really make a lot of interesting things. I don't know if someone has any questions.
Yes, Peter. So when you touch the board, does that call a specific fourth word with like the coordinates of where you're touching, or could you go over that a little?
You want to see my code?
Well, I'm just curious what because it's almost kind of like an interrupt in the sense that if you touch the board.
Look, the code for that is a touch, but I am not with my mouse. Let me put the mouse. I am a bit. There is so much USB here, you can't imagine a lot of things I have. Here, AirTouch here. This is a code. This is the word I am using.
Uh-huh.
And this word needs two variables. One variable is xx and the other yy. What is yy? Here is xx and the other here it is yy and xx. TFT touch, this is the word. And if I will share this with all of you. This is recently, very recent, and here are the where is the word? These are the words for the touch. This one, these two. They get two variables and they give you on the stack. No, they give you you need to feed two variables, and they will return inside the variables the values of the x and y on the touch screen. There is also a third variable possible, so you can have x, y, and pressure. You can read also the pressure, so it's very interesting. There is a lot of I am using a library from Arduino on the ESP32. And this variable, it makes any sense to make this as bare metal, as rough, because it's so much work. Many times these variables are made by a lot of people working during years. So it's preferable to include a library, and you are ready to run with force with this.
And certainly you can raise it to some more abstract level, invoking words depending on the position, and then define a matrix if that's what your application needs. So I think that's the low level access, and everything else can be put on top. Francois had raised his hand, so you probably have a question.
Yes, I think it's really cool that you're still using the block interface. But one thing I do not quite understand is why you need the editor prefix specification for any block operation.
I did not understand, Francois.
It looks like you need the editor prefix for any block-related operation.
Yes, this I posted on the group. This is a trick. Bill Ragsdale, that is a magician, he can teach you a lot of tricks, but I only know this trick about the editor, and I loved it. I will explain this to Brad because Brad probably does not know it. I can share again my screen.
Yeah.
And this is very rapidly, very fast. Brad, I found this one. I put this on the editor. I write editor in the front. I make a list, so I am addressing the block number 28 in this case. And I put in front of my lines, right. This is right line number 0, right number 1, right number 2, etc. Then I do flash, so I can make the copy and paste into the Teraterm here. I can do a paste. When I do a paste, my micro is not plugged in. Let me try to plug this in.
Yeah, well, it worked. So
it was, yes. When you paste this here, it's saved on the block file.
It's editor commands. Yeah. Very nice.
In spite of typing, so you do 28 list and your block is there. It's saved.
Mm-hmm. Nice.
Very nice. Yeah, that's more like the regular interface. Once you're into the editor context, you should have access to those words without prefixes.
Our editor is very simple. It's a single line editor. Have you used ESP32 force, Francois?
Not really.
Oh, I think he's wondering why it's in a separate vocabulary. Is that perhaps?
Yes, actually.
Yeah, I was concerned about filling up the public namespace primarily. I don't know if if folks feel strongly about moving it outside. I guess typically on some forths the editor gets squirreled away in its own namespace, but.
Mm-hmm. Yeah, it's because of some name clashes that you normally have with the editor command. So if the editor has single letter commands like I, you have a name clash. And so that's the reason why it's traditionally in a separate vocabulary.
Exactly.
Yep, that is a big problem. I tried to implement Leo Brody's line editor, and I couldn't because I don't support vocabularies.
Well,
that was a big dismissal.
Yeah, you have to invent other names then. Yeah.
So it goes.
Mm-hmm. Right. Are there any other comments, questions? Rob,
Robin, yes. Go on. Rob.
Sorry, I didn't really have a question. I'm just moving my phone about, so.
Okay. Yeah, that happens. Never mind.
We can move to Brad's presentation then.
Yeah, we do. Yeah, it's nice that the next speaker always is involved in the discussion already. So Brad is our next speaker, and he talks about Telnet news on ESP32 force. Brad. Yep.
Hello. Can
that works?
You hear me? Great.
Yep.
All right. Let me go ahead and talk about a few different things. So I'm going to talk about three different things. It's some improvements that have gone on in the last month or so since I spoke with this group, and then I'll briefly touch on a thing about modules that I was pondering and a thing related to that, and then talk about cryptographic hashing on the ESP32. So a bunch of different changes since April. A lot of them are fairly minor. Things like I noticed I had somehow missed FROT with the floating point support. There was a bug in SF float plus, which it was leaving an extra value on the stack, which I was surprised that I got as far as I did with it being in that broken state. And I noticed an anomaly with R-shift. I had inadvertently implemented a signed right shift instead of an unsigned right shift, which seems to be the more typical pattern. Although, if anyone out there is aware of a convention, part of why I had made that error was that I was making use of R shifts in a context where it was useful to have them be signed, and I'm not sure if there is a standard name for such a thing. I would love to use something. The best I could come up with was AR shift, but anyways, there's been some changes under the hood to work on includes, and I think I'm sort of incrementally working towards a world where files might be used more pervasively on the device. There was already include and included present, but they were sort of inefficient about, or not inefficient. They were different than eForth in the sense that when you include a file and then include a file from that file, the paths were not relative, which can be problematic if you're trying to do something with a recursive include. Part of how I came to be fiddling with that was that I noticed that I found myself having to be very careful with include order and missing the word needs, which doesn't include if the file has not already been included, which is now supported in the innards of the system. I got an email a bit back from Peter about lack of soft AP support. I had in importing the Wi-Fi words just not not included all the software AP related ones. This allows you to have the ESP32 be in a mode where you can treat it as an access point, and just hadn't added those. And then a whole bunch of things have been a problem with the with Telnet and with terminals, and I think I'm at least dangerously close, if not fully there, in terms of being able to work a little bit better with some of the terminal quirks that I've encountered that come up with Telnet. One of the issues is that depending on the Telnet terminal that you use, depending on the if you're connecting over serial or different transports, you end up having different conventions. And I guess I tried to there's a aphorism, be liberal in what you accept and conservative in what you omit. And I tried to do that. It seems that carriage return line feed is the more conservative thing to omit. But then I've tried to have all of the input handling be flexible and tolerate the situations where you're getting just individual carriage returns or carriage return line feed pairs, or line feeds are really weird. When I was noticing some of the Telnet implementations out there seem to, in certain circumstances, send a carriage return followed by a nil as the return value, which is, I never noticed that before. So let's see, let me pivot over. The Telnet, I thought I'd demo just Telnet generally working. I've got a block with my Wi-Fi password, so it's not for all to see. And then let's see if, oops, I'm in an existing session, so I will. So let's say I go to this. So I've started that, but I need to go into the Telnet D. Can't spell Telnet vocabulary, and in there's the implementation, but there's also the server. I'll do Telnet server, and that will run a Telnet server. And oops. Oh, okay. So much for my claims of having all of the terminal woes fixed. That's some awesome demo. Oh yeah. So one particularly odd thing, and others, please email me as you find experiences here. I've noticed that under certain circumstances, at least Linux under Windows seems to do an interesting thing when you connect to port 23. It has a terminal mode where it does some line buffering, which does some that I have not found a good pattern to work around that sort of works cleanly with other things. Interestingly, it does something different if you connect if you use a different port than 23 for reasons that I do not understand. And in that world, then things are working. So if you run into trouble, I guess one suggestion is with Telnet, it seems to be some of the terminals do unusual things, unusual things with ports of the port 23. Let's see. Moving on. A thing I found myself wondering, and the crypto piece I'm going to talk about in a second will highlight this, is that currently I've made extensive use of vocabularies, as was noted earlier with the editor, but also a lot of things are kind of stuffed away in various corners. And one of the things that I've noticed, having used vocabularies, I think more extensively than I've used vocabularies previously, because of all the different things that are pulled into ESP32 I found that it's kind of tedious that they're not there don't tend to be sort of nice patterns that at least that I've been able to find for sort of squirreling things away. And I got sort of similar to the question that was asked earlier, I found myself wondering if a slightly flatter namespace might be good, but then the thing you quickly run into is that there are sort of things that are on the inside of the module and things that are on the outside of the module. And so I found myself wondering about this. There's this old 3-line module system, and thinking about minimalism. This is actually not the original, but this is sort of done in a style that works for ESP32 4th. But I'd be curious if others sort of what your experiences have been with vocabularies. Do they work well for you? Yeah, so I guess, you know, sorry, and this is the style in which this module system is used. It basically provides a way to have a temporary namespace in which you implement a variety of things, and then you decide, you know, which subset you want to actually expose. And I've found myself wondering if this style of module system is simpler and cleaner and might do well for many of the pieces of ESP32 4th that are kind of meant to be on the inside versus the outside. But curious, maybe put things in the comments. Does this module style seem interesting? Does this seem like a thing I should use more in the system, or should I stick with more conventional vocabularies? The vocabularies in ESP32 4th are this weird, they're a hybrid of 479 and 483 style vocabularies. They sort of do the 479 hierarchy, but there are ways to tell them to behave more like 483 vocabularies. And so you can sort of use them interchangeably in principle to sort of the way you would use either of those two. But yeah, but I've also found that as I've used them more, that they feel unwieldy. On to something different. A thing I've been puttering on in the background, and I figured this was as good a moment as any to chat about, was I've been thinking about hashing and hashing implementations. There's in particular, I was looking at two there's SHA-1 and SHA-2 algorithms. SHA-1 is interesting mainly because it's used by Git, and although actually Git is in the process of transitioning off of it, it's no longer considered cryptographically sound. The interesting thing about these algorithms is that they have the nice property that you can hash a thing and then have an extremely high confidence that you've got sort of a unique identifier for it. And I've found myself wondering, well, what would a sort of a fourthy block style sort of analog to Git look like? And so as the sort of first building block down that path, I thought, well, okay, I should have an implementation of SHA-1 and to play around with such things. There's also SHA-256, which is really one of the variants of SHA-2, and it's used by Bitcoin and folks. So that's similar and fun. It's got the larger digest. So anyways, I've implemented both of them, and they're actually sitting, if you go looking around, they're not actually loaded by default in the ESP32 4th, because I don't want to bloat things, but they're sitting in the micro eForth repository if folks are interested down in libs or something. And so an implementation in Forth wasn't bad. There's a bunch of values that are used actually in both algorithms. I kind of have shared a little bit of code between the two. I created a buffer and some convenience words for manipulating that buffer, because each of these algorithms both work sort of a block at a time. I needed to make this work for desktop systems where you've got a 64-bit word size. So in some cases, I need a way to do masking and stepping, adding clip to 32 bits. And then this is another place where, again, maybe post in the comments if you know of any sort of good precedents for this, but I found that I needed or the equivalent of like an x86 roll or RAR, the sort of rotation with wraparound. This is a common cryptographic operation. And then I've got a few words to do endian flipping, because for reasons that are peculiar, the SHA algorithms operate in big endian for a bunch of things. And so it's sort of, probably if I thought about it more deeply, I could sort of compensate it and do things the other way around, but it was easier to just do things with the architecture and then flip them all at the last moment. I've got a convenience word for extracting one word's worth of digits for emitting the digests. And then there's some initialization to sort of arbitrary magic values. They're not actually magical in the SHA algorithm. Because this is the NSA that was the originator of it, they go to great lengths to use constants that are the phrase is, I think, nothing behind my back. So most of them are things like the hex bottom digits of like the square roots of prime numbers or things like that. Sort of arbitrary but not arbitrary constants. And then this is the core of the algorithm, sort of all on one screen, and it's not too bad with sort of that setup. You've got you sort of expand out the blocks. You get 64 bytes of data. You sort of splay that out across a larger 80 word space, and then there's a series of rounds that do various transformations, and there's sort of 4 variants to those rounds where you're doing this common stepping operation that's doing a bunch of scrambling and shifting, and then you're doing some various masking, and again some a sprinkling of arbitrary constants, and then I pull everything out into values, and that's it. And so this chunk operation is just sort of stringing together these 5 phases. This of course only processes a single block, and so then there's a second challenge, which is that if you have a larger piece of data that you want to hash, you have to load it in the appropriate order. You do this by sort of bringing it in, and then this is where I apply my endian shift, and then I've assumed the buffer is slightly larger than I need, because there's when you get to the very end of the block, you need to mark it with a single bit, which I do. Well, I mark it with a single byte because I don't support bit level encryption. And then there on the very last block, you need to sort of tag things appropriately. And so I don't know. There's a buffer for the digest and printing of the digest. Sorry, that was a bit of a segue. And then here's the sort of outer wrapper where you would invoke it. So you pass in a block of data, and you would get out a hash and a length. So sort of byte buffer in and string out. And you walk through, chewing through each chunk one at a time. And then at the very end, you have to handle there's a couple of edge cases around whether you've sort of got a whole block or a partial block. And then these last 2 lines, you're sort of stuffing in the times 8, so the number of bits in the message, and then you can pull out you can format your hash and pull it out. And so I'll demo that in a sec, but sort of at a high level, the way to think of these chunks is that you're sending in the data chunk at a time, and then on the very last block, you're marking the end of the message with a 1 bit, a bunch of zeros, and then at the very end you get the size in bits. And so if you've got the thing that's exactly a multiple of 64 bytes, then this is all the way. You have an extra block just to include that size at the end. But the ESP32 has hardware to do both. This one, which is SHA-1, which I just went through, but also SHA-2. And so I wanted to look into using that hardware. The way that it works is that there are a set of, there's actually a peripheral that handles doing this, and then there's a series of dedicated D-port registers to communicate with it. So you have you can control from the ESP32 the clock of the individual. There's a separate unit for SHAs, a separate unit for AES encryption, and I think one for RSA encryption. And so there's a set of enablement bits for the clock, and then a separate reset bit for the unit. And I believe the underlying idea is that the you save power by turning these on and off selectively. So if you're sort of doing a stream of encryption, you turn it on and so on. There's a buffer of 64, actually, depending on, so it supports all the way up to other variants of SHA-2, which can have a chunk size bigger than 64 bytes, but effectively a 64 byte buffer for the current chunk. And to be clear, that rather than sort of the hardware implementing the entire algorithm, it implements the algorithm just for the one chunk, and then you have to still do the breaking apart of the message into chunks and the tagging of that appropriately. And then there's some control registers. There's one that you poke a 1 into to start the operation, and then for each successive block, you do the continue operation, and then when you're all done, you do the load operation, which will, from some hidden internal register, transfer in the completed digest into the text area. Throughout, what you're supposed to do is every time you do one of these operations, because there's a separate unit sort of handling this asynchronously, before you go on to the next step, you're supposed to check this, read this busy flag and check for it to be done before going on to the next step. This is the theory of operation of this thing. The idea being, right, that you would enable these, you would load each of the 64 byte chunks in, you'd write a start value or continue value for the later blocks, check for busy, write a SHA-1 to load, and then wait for it, and then get the hash in SHA-text. In practice, I'm partway there, and it is a little bit flaky, but it is partially working. Let me see if I can get out of this screen. So do a reset. So the problem that I'm encountering, and I have a couple of theories as to what's going on, but the problem is that this is a shared resource within the device, and the ESP32 sort of libraries that exist in C, they actually wrap the accesses of these registers in a bunch of synchronization, because you have only one of these SHA units for the device, and you have multiple cores. And there are other things going on in the system. So in principle, perhaps why I'm hitting issues is that I am not honoring the synchronization primitives around this unit. I found that sort of freshly loaded, I'm able to get things to work. So if I go ahead and take this bit of code and bring it in, and then here's I've got the individual registers. So this is the sort of the same code that I showed before, but with substituting in use of the hardware. So up here in where is it, in chunk, I'm moving data into the SHA-text register, and then using either continue or start to pump data through, and then at the very end I move data out. One weird quirk I've noticed is that I've got the separate W move word, because that moves things a word at a time, because it seems that character level moves do not make the system happy. It gets confused by character rights. And so then on a fresh load of the thing, fingers crossed, if I do the sort of the simple case of hashing, actually let's try an actual message. So I'll hash hello, and I'll do SHA-1, and I'll type out the result. So and that if we go over here, oops, this is Telnet still. And so let's compare with Python and see if we get the same result. So we'll pull in hashlib, and we'll do the SHA-1 of hello, and we'll print out the hex digest. Oops, and I need to do bytes, and we get the same number. So that's encouraging. However, the discouraging part is that if I go and do this again, I get a different answer. So something is not quite right with the hardware. So I have a one-shot SHA-1 with hardware, and then a random number generator thereafter. So perhaps I'm not doing something correct to reset it, or something else, but work in progress mystery. I'm going to now actively pay attention to the chat, and if there are any questions, please chime in.
Yeah,
we can ask Jason. Sorry, we can ask Jason to test these SHA algorithms, Brad, because Jason has a collection of ESP32. He has different the older models almost.
To be honest, if I suspect that it may be inefficient or ineffective for me to be doing it directly with the registers. I got the sort of odd inkling of, oh, I'd like to understand how the hardware works, but there is a bunch of C entry points for managing these, and probably if I wanted to expose them properly, just exposing them with C bindings would be the way to go. That would probably be smoother in terms of using it as a shared resource, because, for example, some of these algorithms are used underneath when you're doing things like talking to Wi-Fi and so on, because these are algorithms that are used in some of that. And so most likely what's going on here is there's some circumstance where the hardware is trying to share the device. The odd thing is that having sort of dug through the innards of the C library, there's quite a lot of thought that's gone into sort of turning on and off the hardware at appropriate moments. And so on. So it may also be that it has substantial power implications to leave it in a state where the unit is on.
Yeah, tricky. All right. Are there any other comments, questions?
I just have to say that this Ford mobile here is very grateful to you that it can finally come out and play.
Yeah. Right. Yeah, I think we all admire.
I would have a question.
Yeah. Christian, go ahead.
I didn't understand the concept of what module does. It doesn't seem to do the same thing that module does, let's say in Python, or what is the concept of module?
Yeah, so the intention is that imagine that you've got a set of words that are logically a module. The idea is that you have some pieces of some set of words, and that they're the internal implementation of a thing, and then there are other pieces that are the external interface to that thing. And so we're saying Python, the two tend to get blurred together. But if you think of a language like C, where you might have a header file exposing certain visible methods, and then internal to that you have implementation, or in a language languages like Java, you've got private methods and public methods. And so right now, vocabularies, I sort of treat them more like, well, here's this other area where I've got words related to a given topic. I have seen, I imagine one could use vocabularies in a similar fashion, right? Maybe have a vocabulary, and then within that vocabulary have sort of the private words. But it feels like it gets very complicated when you do that using conventional vocabularies. And I've sort of struggled with whether there's something kind of off about it. It can be done, but it also feels like I'm sort of fighting with the name spacing of it. Whereas I've always been impressed by folks that end up with a flat namespace. They have everything sort of out in the open, except for sometimes they'll stash assemblers off to the side, or editors and so on. And it feels like in some ways the decomposing things into vocabularies almost makes things more awkward. So I don't know if that answered your question.
Well, I'll tell you what I got as an understanding of what you're saying. Roughly, module does not load new code; it just makes it visible.
Yeah. Correct. So exactly. Unlike something like Python, where there's an import, and then that's tied to this is just the syntax for the namespacing that you get out of a module. Whereas there's the separate problem of
so it does more or less the same job as vocabularies, but in an easier way to do it.
Yes, sort of a simplification of it. For modules in the Python sense, the functionality I just added with needs is actually probably the closest analog. And that actually I'm not too sad about. Basically, the idea is that if you have a piece of code and you want to use it and you know that that piece of code sort of needs to only be used once, multiple different places can say needs and then some file name, and then they pull it in, and if multiple different parties pull in that same piece of code, it will only get loaded once. And so in that sense, needs is probably a closer analog to at least the module loading portion of Python.
Yeah, so there are actually different approaches like packages or module. I posted some links in the chat, and there's also the way that Albert Niehoff from the Dutch does it. He has just a inside vocabulary, and all the things that get stuffed away are just inside. It's a mess, but you separate the visible things and invisible things by this.
This is inside. This is not per vocabulary. Is it sort of there's each vocabulary and then an inside vocabulary for all the junk?
No, he has a global inside vocabulary, forth and inside. And, so inside for the words that are used for constructing others and that are not intended for further use. Right. Are there any other questions? No. So then I'm happy to announce our last speaker and welcome Howerd to the meeting. I'm very happy that you made it, and you can review the things, the amazing things that happened before on YouTube later. Well, we are looking forward in your further explanation on Colorforth, which is still very, very amazing. So,
well, thank you. I have to put my Colorforth background image back up. I wasn't intending to talk about Colorforth this time, but I can.
So, that's at least what I have here on the schedule.
Okay.
Yeah. So I don't know what.
No problem.
Ulrich, no problem. If Howerd, there is no problem. The meeting was amazing today, and a lot of participants. So if you want to shift this for the next meeting, it's perfect. It's no problem.
That also would be fine. And Colorforth doesn't go away, so
yeah. No, it won't go away. I could show you Colorforth windows that I'm working on. This would be very quick. What's been happening? I've just had family over, so I haven't been able to attend most of the meeting, but I'm catching the tail end. And I haven't had much time over the last couple of weeks and to prepare a PowerPoint. So this is just going to be showing you a program and see what people think.
Howerd, one question. You have been in the sun and you look very colorful also.
I have been in the sun. I've been on holiday to England and there was lots of sunshine and not much rain.
You have taken a bit of color. Wonderful.
Yeah. Well, I'm trying to get myself lit correctly as well here. I've had to close the blinds on the windows because there's beautiful sunshine coming in, and that's it's very nice outside, but it ruins the video. Obviously, I even have a colorful LED light here. I can probably one of these options is to change the color. So how about that? Various colors I can introduce. But, anyway, sorry, this is not talking about Colorforth, to talk about my color. Yeah, so completely unprepared. I will just launch a program that I did a couple of years ago. If I can get to it quickly, and then I'll share my screen. Well, I thought I clicked it. Okay. Unbelievable. Let me. It's quite incredible. I click on an executable and nothing happens. I think Zoom or whatever this, yes, Zoom must take quite a lot of processor resources. I will remain calm and try and defeat the curse of the demonstration. So first I will share my screen and you can see all the problems I'm having. Okay. Then I need to find the program that I want to run. This is very strange. Okay, what I'm going to do here, I know what's wrong. I did an edited version that works without a comms port, especially so it would run, but this version exits have come out. So this is, start again here, just edit this all out. You're watching on the video, fast forward, right. Colorforth win.asm. This is Colorforth style program running under Windows. It makes Windows calls rather than trying to write directly to the hardware of the PC. So this is a whole different angle on things. Okay, so somewhere in here there is serial open. Even my editor doesn't want to behave. It's amazing. Okay. That out of the way here. Fine. Serial. Oh, there it is. Right. Serial open. And this is being called here somewhere. Where is it? Serial open. So I have to comment that out. That's the first thing. I have to find out what the version of this is. February 2021. So this is over a year ago now. Right. So now I have to rebuild the system. And for everyone who works in the kind of environments where I normally find myself, you don't have to wait 5 minutes for this. I have to find the folder that I just opened that has that program in it. I'll close all the others. This is what happens when I don't have any time to prepare it. So this is this one. Can't be very many. I'm just picking them randomly. Oh, there it is. Right. So now I have to recompile, and you recompile by clicking on go.bat, and it's running an assembler, the goasm.exe assembler, and there it goes. And it should actually run this now and come up with a screen. It will complain that it can't find a comms port. Maybe. Okay, maybe not. Right. So this is as far as I've got with this. This is a simple terminal. It's handling key input from a window. This is from an assembler thing. And this shows that you can type Unicode characters. I don't know whether I've shown this before in the Fourth Cafe, maybe some time ago. So there's also some other functions here that connect to a comms port. And I'm using this as a kind of a test bed to try various ideas out. So what you've got here is a fixed font. You've got a fixed screen size, just as you have in Colorforth. And I'm using the Windows write to screen calls to write things. So this is all very easy. You've got the full power of Windows. You can make any sort of call. And yeah, if I had a comms port connected to a terminal, then I could show that it's actually acting as a terminal. Okay, now the point I'm showing you this, and I want to ask everyone for some advice as well, is I want to replace the Win32 fourth F kernel, which is like the fourth kernel.exe, which is created by, because it's C source code or C++, and you have to have a C compiler. And I don't have a problem with C compilers per se, but if you use an assembler like goasm.exe, it's 133K. And I think if you can get away with a C compiler that's 1,000 times bigger than that, then you're doing well. I think it's more like 4,000 or 5,000 times bigger. Because I always like to just have everything that you need in the same folder here. So if I go back to the assembler for this, it's a bit hard to see an overview here, just scrolling through code. I hope you can read my editor font. You have to bear in mind everything's very slow as well. So this whole application is something I got from the GoASM website. There's lots of applications, and they demonstrated a Unicode UTF-16 Windows program. So this is what this is based on, and I've added a few bits to it, like a COM port and so on. Now, what I wanted to show here was, I think it's called Quad Byte, if I remember rightly. This is going back a year. Oh, good, my memory's still working. So I've got something called Quad Unicode Emit, which is a kind of, it's a 32-bit version of a character. And obviously this has got to harmonize with the 32-bit Colorforth character, if I want to call it that. And so the complicated bit of the code here is that I construct a 4-byte packet. So every character that you type here, for example, so I do ABC, you're going to get, actually there were some funny ones I put here. There's the random ones. I'll have to look through the code to find out how to do these things, but there's some control characters that do some interesting things. Just try a few random ones here. Yeah, there was something that showed the font. So the point is, I'm trying to create. This came out of an idea. I wanted to make Colorforth run under Windows without having to use a virtual machine. Therefore, it'd be 100 times quicker, and everyone could still see what it was like and use it. So I'm now thinking, I'm wondering if it's possible to use the GoASM assembler to convert the Win32Forth, which I should have somewhere open around here, F kernel. So how Win32Forth works is you've got some, oh, it's just not in there. Hang on a second. In here, there should be, no, sorry, I've got to hunt it down on my computer. I put it somewhere else. There you go. So this is actually the Win32Forth system that I got from my brother Rod, who worked with Win32Forth some years back. And again, this is not where it is. So you've got an fkernel.exe. Let me run that. This is the normal way that Win32Forth boots up. Okay. So what you've got here is a very, very simple terminal, which you can do simple things in a normal Forthright way. And when you construct the full Win32Forth system, it starts off with an F kernel and it adds to it. So if I run the, what is it, the Win32Forth exe here. Yeah, right. So what has happened is that it's this system is basically the F kernel, which then loads more Forth words and creates a more complex terminal. So what I'm thinking is, rather than having C++ file and a C compiler to create this F kernel, which is this one, I want to replace that by an assembler thing, and this connects with the Windows version of Colorforth that I was doing, which has exactly the same functionality. You've got to open a window in Windows. You've got to be able to write characters to it and so on. And what I want to do is to extend the assembler version of fkernel so it automatically loads a Forth file. This is the way the old polyforth systems worked, where you have pf.com, and that would open a normal Forth console, black screen, and then you would type hi, and hi was defined as 9 load, and it would load block 9. So what I would do here is I would have something that either has hi within this fkernel, which would load Forth system.f or some such, or you could call it hi, which would do that for you, or I'm not sure, but there's lots of options. So I'm trying to investigate for both of these things, the fkernel.exe for Win32 Forth and for my Colorforth under Windows, a very simple assembler-based Forth. And so what I was hoping to do is to ask anyone for information. What's the best x386 32-bit Forth system written in assembler? And let's see what happens. And I think that's it for me from now. And maybe just if people want to ask questions or answer my question, that would be great. I've looked at MinForth. That's my current favorite. And of course, I've got whole swathes of Forth words implemented in assembler in Colorforth, but I'm not sure it's that's the easy route to go because it lacks lots of things. So Ant's Forth would be nice. MinForth is not quite Ant's, I believe, but it's close. Okay, over to you guys. I will come back to the Zoom thing, hopefully, and see whether anyone's actually heard me saying anything, because I've not heard anything recently. Are you all there still? Or I lost contact.
Oh, we're hiding.
Good. Fantastic. I will stop sharing. Okay, so can anyone answer my question? Can anyone recommend a good PC type 32-bit Forth? Joss, yeah, I thought I was going to ask you and Albert as the first two ports of call.
Hello.
Good question.
Hi.
Do you use Win32 for the old version as the working horse for your old programming?
Sorry, can you say that again? The sound went funny.
Are you the one use Win32 for the old version for all the Forth programming? I'm using it for all my Forth programming as a cross compiler. The old version is 4.2672. The new version is 6.15. Because of the old version cannot operate under Win1310, 3264 system, but mine can. But I wonder if you work it under Win10 or 64-bit or not.
Okay, this is a whole can of worms you're asking about here. That's the original Win32 Forth version 4.x. It works fine. If you want, okay, my brother Rod, he created or updated 15 years ago 4.4, I think, or whatever it was you just saw on the screen here. Yeah, 4.4, which is a great number for a Forth system. And he's been keeping that quietly updated. And I was on holiday in England a couple of weeks ago, and we visited him and stayed with him, and we talked about Forth, and he explained about this, and I said, "Can I have a copy?" So this is it. So, and I'm comparing his copy with mine. I support version 6.05H. Which was the last version that did not upset antivirus programs. After that, the architecture was changed in some way that I don't fully understand to make it look as if it was a virus. yeah, so 6.15, which I think is the current one, I can't use. It gets taken off my system, any system I put it on, so it's not viable. So I'm trying to go back to square one here, and I'm starting with the F kernel, because when I want to change the F kernel, I went into 2/4. As I did, I wanted to make the it possible to have a wider window. I had to ask my brother to recompile it for me because it needs Visual C++, is it called, version 6 anyway, from what must it be, about 30 years ago. And he has a Windows XP computer that he still has it on, and he can recompile it. And my Windows XP laptop died, so I have to ask him to do that. So this is, for me, is kind of unacceptable is the word. I mean, I feel very strongly that you shouldn't use or distribute a system that takes such an effort to recompile, and to find a computer with an operating system that can run a compiler from so long ago. So I'm thinking, what can I do about this? I try to port, what's the word? Upgrade? What's the word? They have a word when you do this. On Visual Studio 2019, I tried to import the VCC, what's it called? VC++ version 6. I tried for a few hours and I gave up. It was horrible because you're not allowed to do certain things these days. So yeah, I'm thinking about that. So now, what was your question, Holly? I couldn't quite. Have I answered it?
Yes, actually, 6.5 is not very easy to use, but the old version can be used. But if you want to transfer from old version to 64-bit system, it's tricky.
It is. It's horrible.
You want to run that program, you have to compile under the old version, like HP system. Then you transfer to the executing code to the 64 system, Windows 10. That way, it can be work very easily. And I use it for all my MCU cross compile system for many MCUs, and it's very tricky.
Yes,
to use it.
It is, because there's some fundamental changes to the architecture between version 4.4 at least and or 4.2, I think you said, and version 6.15, which is the current one. And those changes are things like when you want to call a Windows call in the older versions, I say, then you have to put the word call and then the Windows function name, and that has to be defined somewhere as well. Whereas in the newer version, when you import the Windows functions, they automatically compile a call, or in some way it works so you don't have the word call in front of them. And the other thing is this abs to rel and rel to abs, that the older Win32 systems have. I did understand this once, I've forgotten what it is, but they have a memory map that means certain things are absolute, certain things are relative to your system, and you have to scatter these words everywhere and know where they are. So these are things I would like to avoid if I can. So I'm having a rethink about this to see firstly if you can use an assembler version of the kernel, because I think that would be really neat. And I don't know if there's any issues that Microsoft C compilers, do they know something secret about how to create an executable that means that it's accepted by the Microsoft world? It won't get deleted by your Windows operating system or classed as a virus by an antivirus program. So I don't know whether I'm asking a question or answering one there, but over to you, Holly.
Actually, I can use this for all my design, including the graphic, even the hyper terminal, even the terminal as the terminal. So it can be used very easily, very very widely in all my applications. Thank you.
Yeah, that's good. Could you possibly post a link to it? Is it something that you publicize somewhere?
Actually, I published in the GitHub, so if you want, you can see there. And
please,
if you could.
Okay. Would that be under your name then? Maybe you could just post a link in the chat here, so I could have a look, because I didn't know about this.
Okay.
That would be very good. I mean, maybe.
I'll post it.
Yeah.
Yeah. Okay. Thank you for your supporting.
Thank you for your support. That's brilliant.
Actually, I designed the assembler, disassembler, and cross compiler. You know, the disassembler is automatically generated by the assembler.
Oh, I think I saw that.
Last week.
Yeah, I saw that.
And the assembly is very easy. Once you know how to fill the blank, then you can design the assembler. It's quite different from the traditional one. You know, people want to design the assembler. It's hard, tedious work. But the assembly don't have to design it anymore. So it's quite
Atle, go on. Yeah. No need to raise hand. We are already in the fourth cafe, I think.
Okay.
Oh yeah, it was
speed things up a bit.
It was just about how to not get flagged as a virus, because a friend of mine, he was building antivirus software, and what he did, he looked